Have you ever felt that cold shock of a metal doorknob on a really frosty morning, even though it's been inside all night?
Oh, yeah. Or seen those, dramatic videos online, railroad tracks buckling in the summer heat.
Exactly. These aren't just random things happening. They're
Hmm.
actually everyday demonstrations of these powerful, unseen forces at play. We're talking about the thermal properties of materials.
Hmm.
Today, we're taking a deep dive into this, well, really fascinating world. We'll explore how materials respond to heat.
And how that influences, everything from your morning coffee cup, why it stays warm in one kind but not another.
Right. All the way to critical components in aerospace tech. This isn't just theory, it's the actual science behind why stuff behaves the way it does when temperatures change.
Yeah.
And it's surprisingly impactful in our daily lives.
Yeah, definitely. So, our mission for this deep dive is basically to unpack the core concepts from the chapter on thermal properties in Callister and Rethwish's Materials, Science, and Engineering.
Great resource.
It is. We'll break down the key ideas, the terms, the examples, try to present it clearly so you can grasp these vital insights without needing the textbook open right there.
Think of it as your essential guide, right?
Mm-hmm.
Understanding heat capacity, thermal expansion, thermal conductivity.
And thermal stresses, which are a big one.
Absolutely.
Hmm.
We're going to journey from the minuscule world of atomic vibrations, these
Mm.
tiny jiggles,
Yeah.
all the way to the big picture, the macroscopic effects, stuff like bridges expanding or why a glass dish might shatter.
Get ready for some aha moments
Uh-huh.
because the explanations are often, well, quite cool.
Okay, let's kick things off. First core concept, heat capacity.
Right.
At its heart, heat capacity is sort of a material's ability to act like an energy sponge, absorbing heat.
Yeah, it tells you how much energy you need to put in to raise a certain amount of that material by, say, 1 degree.
Mathematically.
Conceptually, yeah, it's the ratio of energy change, call it dq,
DQ, okay.
to the resulting temperature change, dt. So C equals dq over dt.
Simple enough?
And when we talk about specific heat, that's just the heat capacity per unit mass. Often more practical, for calculations.
Gotcha.
Now, what's really fascinating is how solids actually absorb this energy.
It's not just getting hotter, right? There's a mechanism.
Exactly. It's mainly through the increased vibrational energy of their atoms. Atoms in a solid, they aren't static, they're constantly jiggling.
Always moving.
Right. But they don't vibrate independently. The vibrations are coupled through the atomic bonds, creating these traveling lattice waves.
Okay, so picture like a ripple going through a tightly packed crowd.
That's a great analogy. You push one person, the motion carries through. These coordinated vibrations are essentially elastic waves, like sound waves.
But different scales.
Yeah, very short wavelengths and super high frequencies. And we call a single quantum of this vibrational energy a phonon.
A phonon. Like a photon for light.
Exactly. But for mechanical vibrations in the lattice. And these phonons, they're incredibly important, not just for heat capacity, but also for how heat moves, which we'll get to.
So if materials absorb energy through these phonons, I guess you'd think heat capacity just goes up steadily with temperature. But you said it's not quite that simple.
It's not quite linear, no. It's a great question. If you plot heat capacity against temperature, you see this distinct curve. At absolute zero, 0 Kelvin, there's basically no vibration, so heat capacity is zero.
Makes sense.
Then it rises really rapidly with temperature. At very low temperatures, it actually follows a cubic relationship, C sub V equals A times T cubed.
Wow, okay. But it doesn't just keep climbing forever.
No, it doesn't. That's the interesting part. Above a certain point, we call it the Debye temperature, the DD.
Debye temperature?
The heat capacity actually levels off. It becomes essentially constant.
So wait, even if the material is getting hotter, the amount of extra energy needed to raise it 1 more degree stays the same?
Pretty much, yeah. Beyond that Debye temperature. For a lot of common solids at room temp, this value is roughly 25 joules per mole Kelvin. It's a surprisingly good approximation. Now, these atomic vibrations, the phonons, that's the main way solids soak up heat. But there are other small contributions.
Like what?
Well, electrons can absorb some energy, and in some magnetic materials, randomizing electron spins can add a bit at specific temperatures, causing a little spike, but usually those are minor compared to the phonons.
So the big takeaway here, a material's ability to store heat is tied to these atomic vibrations, these phonons, and actually levels off once things get energetic enough.
You got it.
Okay, building on that idea of atomic movement,
Hmm.
let's shift to something super relatable. Thermal expansion.
Yes. Things getting bigger when hot, smaller when cold.
You know it. It's why roads crack in the heat, or why, like you said, that old canning jar lid gets stuck or maybe loosens up under hot water.
And we can put numbers on this. For linear expansion, the fractional change in length delta L over L0.
The original length.
Right. That's directly proportional to the temperature change, delta T. And the constant linking them is the linear coefficient of thermal expansion, alpha.
So call E0 nec T.
Precisely. And similarly for volume changes, there's a volume coefficient, alpha V, which for many material is roughly 3 times the linear one.
Okay, makes sense dimensionally, but why? On an atomic level, why does a material physically get bigger? It's not just atoms vibrating more and needing more elbow room, is it?
This is one of those cool aha moments. It's a bit more subtle than just bigger vibrations. Think about a plot of potential energy versus the distance between two atoms. It looks like a trough or a well.
Okay, I can picture that. Lowest energy at the bottom.
Exactly. At low temperatures, atoms vibrate near the bottom. Heated up, their vibrational energy increases, they vibrate with larger amplitudes. But here's the key. That potential energy trough is asymmetric.
Asymmetric, how so?
It's steeper on the side where you push the atoms closer together, the compressive side, and shallower on the side where you pull them apart, the tensile side. So because of that asymmetry, as the atoms vibrate with more energy, their average distance actually increases. They spend a bit more time further apart.
Whoa, that's clever.
Yeah.
I just figured they vibrated more, took up more space. But it's the shape of that energy, well, the asymmetry, that forces the average distance to increase.
That's exactly it. If the curve were perfectly symmetrical, perfectly parabolic, there'd be no net change in average distance, no thermal expansion. It's all about that imbalance.
Mind blown.
Okay. And this asymmetry also explains why different materials expand differently. Stronger atomic bonds mean a deeper, narrower energy trough.
So less room to move outwards.
Right. A smaller increase in the average separation for the same temperature rise, which means a smaller alpha, a smaller coefficient of thermal expansion.
So what are the trends? Like polymers versus metals versus ceramics?
Generally, polymers have the largest expansion coefficients. Think 50 to 400 times 10 to the minus 6 per degree C. Those long chains are held by weaker intermolecular forces.
Okay, makes sense. Metals.
Metals are intermediate, maybe 5 to 25 in those same units.
And ceramics.
Ceramics generally have the lowest values, maybe 0.5 to 15 times 10 to the minus 6. That's because of their strong ionic or covalent bonds. Fused silica, quartz glass, is remarkably low, around 0.4, partly due to its atomic structure.
Okay, but here's where it gets really wild. Back in the 1890s, right? A scientist, Guillaume,
Charles Edouard Guillaume, yeah, Nobel Prize winner.
he discovered an iron-nickel alloy called Invar that has almost zero thermal expansion over a pretty decent temperature range. How does that even work?
It's amazing, isn't it? And it's not because its energy well is suddenly symmetrical. It's actually related to its magnetic property.
Magnetism, how?
As Invar heats up and naturally tries to expand thermally, there's a subtle contraction effect associated with its ferromagnetism. It's called magnetostriction. And this magnetic contraction basically cancels out the thermal expansion.
Wow. So magnetism is fighting thermal expansion to a standstill.
In that specific temperature range, yes. Above its Curie temperature, around 230 degrees C, the magnetic effect fades and it starts expanding normally.
That is fascinating. And there are others too, like super-Invar.
Yep. Super-Invar has an even lower alpha, but over a narrower temperature range. And then there's Kovar, an iron-nickel-cobalt alloy.
What's special about Kovar?
It's specifically designed to have almost the exact same thermal expansion as borosilicate glass, like Pyrex.
Ah, so you can fuse them together, like for vacuum tubes or electronics, without the joint stressing and breaking when the temperature changes.
Exactly. These controlled expansion alloys are critical for things needing extreme dimensional stability. Precision instruments, optical systems, thermostats, even things like tanks for storing liquefied natural gas, which see huge temperature swings.
Okay, this leads perfectly into a little concept check. Think about that canning jar again. Brass lid on a glass jar. You heat it, the lid loosens. Why?
Because brass has a higher coefficient of thermal expansion, alpha, than the glass.
Right.
So when heated, the brass lid expands more than the glass jar rim, making it looser.
Okay, but what if that lid were made of, say, tungsten, which has a much lower alpha than glass?
Interesting reversal. If the lid were tungsten, heating it would cause the glass jar to expand more than the tungsten lid.
So it would tighten.
It would actually tighten, yes. That difference in material response is key.
Okay, so the core idea from thermal expansion, materials grow or shrink because their atomic energy wells are asymmetric. And engineers cleverly use these differences, even magnetism, to create materials that don't change size much.
Precisely.
Okay, so we've seen how materials change size with heat, but how quickly does that heat actually move through them? That brings us to thermal conductivity.
How efficiently heat gets transported from hot spots to cold spots.
Yeah, think about touching a metal spoon versus a wooden spoon after they've both been sitting in hot soup.
One feels much hotter, much faster.
Oh, right. Why?
That property is thermal conductivity, usually denoted by K. We talk about heat flow as flux, Q, that's heat per area per time. And this flux is proportional to the temperature gradient, dT/dx.
How steep the temperature changes over distance.
Exactly. The equation is Q equals KD, ADX. The minus sign just reminds us heat flows downhill, from hot to cold.
Okay, so what carries the heat? What are the mechanisms?
In solids, it's mainly two things. Those lattice vibrations, the phonons we talked about,
Our friends, the phonons.
and free electrons. The total conductivity, K, is the sum of the lattice part, K sub L, and the electronic part, K sub E, so K T L plus K. Usually one dominates.
Okay, let's compare materials again. Metals are famous heat conductors.
Absolutely. In pure metals, it's the electrons doing almost all the work. K is much bigger than Ka.
Why are electrons better at it?
They move much faster than the lattice waves, and they're less easily scattered, at least in pure metals. Since metals have tons of free electrons, they're excellent thermal conductors. Values are typically, say, 20 to 400 watts per meter Kelvin, high numbers.
And isn't there a connection to electrical conductivity here? The Wiedemann-Franz law?
Yes, a really important link. Since free electrons carry both electrical current and thermal energy, there's a theoretical relationship. Thermal conductivity divided by electrical conductivity times temperature should be a constant, L.
LK.
Exactly. And the theoretical value for L matches experiments for metals really well. It's strong proof that electrons dominate heat transfer in metals.
But interestingly, if you alloy a metal, like making brass from copper and zinc, the thermal conductivity goes down. Why?
Same reason electrical conductivity goes down. Those added impurity atoms, the zinc atoms in the copper lattice, act as scattering centers for the electrons.
They get in the way.
They disrupt the electron's smooth flow, making them less efficient at carrying heat. If you plot conductivity versus composition for copper-zinc, you see a clear dip.
Okay. What about ceramics, then? We think of them as insulators.
And mostly they are. Ceramics are non-metallic. They lack abundant free electrons. So here, heat conduction relies primarily on the phonons, the lattice vibrations.
But phonons aren't as good as electrons.
Generally, no. Phonons get scattered more easily by lattice imperfections, green boundaries, things like that. So ceramic thermal conductivities are much lower, typically 2 to 50 K.
And glass. Amorphous ceramics.
Even lower, that disordered, non-crystalline structure scatters phonons very effectively. So glass is a pretty good thermal insulator.
How does temperature affect ceramic conductivity?
It's interesting. Initially, as you heat most ceramics up, their conductivity decreases.
Why is that?
The increasing lattice vibrations interfere with each other more, scattering the phonons more efficiently. But then, at very high temperatures, another mechanism can kick in, especially in transparent ceramics.
Which is?
Radiant heat transfer, heat radiating through the material itself, that can cause the conductivity to actually start increasing again at high temps.
Huh. And does porosity matter, like little air gaps?
Oh, hugely. Porosity dramatically reduces thermal conductivity. Heat transfer across those pores, especially if it contains still air, is very slow and inefficient.
Air is a terrible conductor.
Exactly. Air's conductivity is super low, like 0.02 Wohlmening SK. And convection within tiny pores doesn't help much either. That's why many thermal insulating materials, like refractory bricks or ceramic fibers, are deliberately made porous.
Right, trapping air. And finally, polymers, plastics.
Generally very low thermal conductivity, around 0.3 Wohlmening K typically. Here, energy transfer is through vibrations and rotations of the long-chain molecules.
Does structure matter, like crystalline versus amorphous polymers?
A bit. More crystallinity usually means slightly higher conductivity because the chains are more ordered, allowing for more coordinated vibrations. But they're still fundamentally poor conductors compared to metals or even many ceramics.
So they make good insulators, too.
Definitely. And just like ceramics, you can make them even better insulators by foaming them, introducing tiny gas-filled pores. Think foamed polystyrene, like in a disposable coffee cup.
That makes perfect sense, and it explains that common experience. On a cold day, a metal doorknob feels freezing, but the plastic steering wheel in your car feels, well, not warm, but not as bitingly cold.
even though they're at the same temperature.
Right, the metal just yanks the heat out of your hand much faster because its K value is so much higher.
Exactly. High conductivity means fast heat transfer.
Okay, so key insight for conductivity.
Mm-hmm.
Heat moves via electrons, fast, efficient in metals, or lattice vibrations phonons, slower, easily scattered, dominant in ceramics polymers. And things like impurities and pores really affect how well heat gets through.
You've nailed it.
Right, all these temperature changes, the expansion, the heat flow,
Mm-hmm.
they can lead to something else. Thermal stresses.
Yeah, stresses induced purely by temperature changes, and they can be a really big deal, can cause fracture, unwanted warping.
How do they arise?
Well, think of the simplest case. A rod held rigidly at both ends. If you heat it, it wants to expand, right? Based on its outfall.
But it can't, it's fixed.
Exactly. That restraint prevents the expansion, and instead a compressive stress builds up inside the rod.
And if you cool it,
It wants to contract, but again, it can't, so you get a tensile stress.
is there an equation for that stress?
Yep, pretty straightforward one. The stress, sigma, equals the material's modulus of elasticity, E times its coefficient of thermal expansion, alpha times the temperature change, delta T. So, EO, T0, TF.
So a stiff material that expands a lot will build up more stress for the same temperature change.
Exactly. If you took a brass rod, held it rigid, heated it by, say, 86 degrees C.
From 20 to 106 C, like in the book's example.
Right. You generate a compressive stress of 172 megapascals. That's significant. That's a lot of internal force just from heating it up.
Wow. Okay, that's restrained expansion. What about other ways?
Even if something isn't held rigidly, rapid heating or cooling can cause internal stresses. Imagine heating a thick slab quickly. The outside gets hot and expands first.
Well, the inside is still cool.
Right, so the expanding surface is constrained by the cooler interior. This puts the surface in compression and the interior in tension.
And rapid cooling.
Reverses it. The surface cools and tries to shrink faster than the still warm interior. Now the surface goes into tension and the interior into compression.
Ah. And tension is usually worse for brittle materials, right? This sounds like where things get critical.
Precisely. This leads us to thermal shock.
Thermal shock. Sounds bad.
It is, especially for ceramics. Metals and many polymers are ductile. If they experience these thermal stresses, they can often just deform plastically a bit to relieve the stress. They bend instead of break.
But ceramics don't bend much.
No, they're brittle. They don't have those mechanisms for plastic deformation. So if those thermally induced stresses exceed the ceramic's fracture strength, it just cracks catastrophically. That's thermal shock.
And cooling is often worse.
Generally, yes, because rapid cooling puts the surface into tension. Cracks initiate and propagate much more easily under tension than compression in brittle materials.
So how do we design materials, especially ceramics, to resist this thermal shock? What makes a material tough against sudden temperature changes?
Good question. We talk about thermal shock resistance, or TSR. To maximize TSR in a ceramic, you want a combination of properties.
Like,
You want high fracture strength, obviously, so it takes more stress to break it. You want high thermal conductivity, K, so heat can dissipate quickly, reducing those temperature gradients.
okay, strong and conductive. What else?
You actually want a low modulus of elasticity, E, so it's less stiff and doesn't build up as much stress for a given strain. And crucially, you want a low coefficient of thermal expansion, so it doesn't try to expand or contract much in the first place.
Low E and low alpha. Got it. Is there, like, a parameter for that?
There's an approximate parameter, yeah. TSR is roughly proportional to U, E, 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 O. Maximize the top, minimize the bottom.
Okay, that brings us right back to the kitchen. Regular glass baking dish versus Pyrex.
Perfect example. Regular soda lime glass has a relatively high alpha, maybe 9 times 10 to the minus 6 per degree C. Take it hot from the oven, put it on a cold counter, bang, thermal shock.
Yeah, I've seen that happen. It's not pretty.
No. The borosilicate glass Pyrex adds boron oxide, BeOros, to the mix. This significantly drops the alpha down to about 3 times 10 to the minus 6.
Much lower expansion.
Much lower, making it far more resistant to thermal shock. That's why it's great for bakeware, labware, anywhere you get rapid temperature changes.
Are there other ways to improve TSR?
Sure, you can sometimes introduce porosity, or maybe a second phase that's more ductile. These can act to interrupt or blunt cracks if they start to form.
Okay. So the key takeaway for thermal stresses, they come from restrained expansion contraction or rapid temperature changes creating gradients. Brittle ceramics are especially vulnerable, leading to thermal shock. But we can design for resistance by choosing materials with the right combo of strength, conductivity, stiffness, and especially low thermal expansion.
Like Pyrex.
Exactly right.
Wow, okay. We have really covered a lot of ground today. It's amazing how these concepts connect.
It is.
From, the tiny jiggles of atoms defining heat capacity.
The phonons.
Right, the phonons. And how the asymmetry in their energy wells causes thermal expansion.
To how those phonons and electrons carry heat, determining thermal conductivity. And finally, how all that can conspire to create stresses that can literally break things apart. Thermal shock.
It really makes you look at everyday objects differently. That creak your house makes when the temperature drops.
Totally. It's all just materials responding to heat, expanding, contracting.
Yeah, and what's really cool is thinking about how engineers use this knowledge. Understanding these fundamental properties lets them choose and even design materials for specific jobs.
From insulating a building, the building a spacecraft that has to survive, what, hundreds of degrees of temperature swings?
Exactly. It really pushes us to think. How can we manipulate these properties even further? What future challenges, extreme environments, new technologies will demand materials with even more tailored thermal responses?
A really provocative thought to end on. Where can we take this next? Well, this deep dive was made possible by the fantastic insights in Callister and Rethwish's Materials Science and Engineering, specifically the Thermal Properties chapter, all brought to you by the Last Minute Lecture team.
Great resource.
It really is. We hope you feel a little more informed now, maybe a bit more curious, and definitely ready to spot these thermal phenomena happening all around you.
Hopefully fewer cracked baking dishes, too.
Let's hope so. Thank you so much for joining us on this exploration.
It was fun. Until next time, keep learning.